Right. Sorry, they just switched this cable around on me. Right. Okay. So this week we're going to cover chapter 4 and 5 in the book. It may be going crazy fast. It is a lot of reading. So when you're reading through the textbook, especially like on the math duration stuff that the author does, don't worry too much about that. Because typically this class, these two chapters are actually usually like covered in 3 weeks. So that's the way I was taught. The problem is that at Stan State, we try to squish the analog and digital together. So this is the stuff that I'm trying to just kind of give you like the idea and the concept about. We're not going to go into the minutia of all the calculations, okay? But it is important for you to get an idea, how does a transistor actually work? And the introduction to semiconductor will take us up to that point, and that's why we're trying to cover this in 1 week instead of 3, so 3 times the speed. But then, hopefully, we stay with the conceptual stuff and not a lot of the calculational stuff. Okay. All right. And the reason this is so important is because, like, basically everything we do every day, all of the 20th century and the 21st century that we are in now, right, is based on this idea of semiconductors slash transistors that you might have heard these names, but maybe you haven't read the Wikipedia article on how they actually work. Okay, so semiconductor is basically all of modern day technology, and so for example, can you guys give me some examples of where you would find a semiconductor, especially? I'm sorry. Right, your cell phone. Well, which part of your cell phone?
That's a great question.
Yeah, which part of your cell phone?
Like, get the battery.
The battery is actually not a semiconductor. Actually, it's like a little chemical battery. Yeah.
Charger.
The the charger probably does have a semiconductor in there. Yeah. The charger, right? Probably has a diode in there. What's inside? What's the most important? What's the most expensive part of your cell phone besides your cell phone plan?
The screen. The chip.
The chip. Yeah. So the processor, right?
Yes.
Right. And the processor reads things from like RAM. You know what a RAM is, right? Or slash memory, right? And a lot of the what's the analog electronics, basically, how does it receive Wi-Fi signal versus cell signal, right? All of those are actually still based on semiconductor technology, and we're going to see how we can learn the kind of like the basic gist of it, so that we actually know how all this stuff works without going into a lot of details about making it highly efficient or really great. You want your silicon yield to be 99.999%, because getting that last 0.9% will save Intel like $10 billion every year, that type of stuff, right? Because you make so much of it, it makes a big difference just by making it slightly more efficient, right? Okay. And semiconductor, all right, so I like to think about it. So I think a lot of people say that semiconductor is, some sort of material that's halfway between a conductor and insulator. Okay. And conductor does what? Anyone remember from general physics?
Conducts electricity.
Yeah, allows charge to move freely around, right? And an insulator does not, right? If there's a positive charge stuck on a piece of glass, it's going to stay there until you touch it and remove it, right? Or if you put it on a piece of metal, that little charge is going to roam around on that little piece of metal wherever it wants. Okay? And semiconductor could be defined, a lot of people on the internet does define it as, well, the charges are kind of able to move around, but not that much. The way I like to think about semiconductor is that it's a material where you can actually control how conductive it is. Okay? And it's actually why they are useful, because you can actually control how conductive a piece of material. You can turn a piece of metal into a glass by just flipping a switch. That's a pretty cool technique, right? So all of this comes from physics and our understanding of atoms, okay? And it relies on both the Bohr model of, well, technically it does require on the quantum model of the atoms, which is stuff I don't expect you guys to know. But maybe the Bohr model of the atoms where you have a nucleus and then a bunch of different energy levels. Everyone has heard of that. We don't need to do a review of that. Okay. So basically, if you're thinking about atoms, think about this model for now. Okay. I'm gonna I'm gonna utilize the quantum mechanical level where it's basically an overlapping wave function, but we're gonna skip all the math. I'm just gonna tell you what happens in that case. Okay. So if you haven't heard about that, that's okay. Okay. So if you have a positive charge and a negative charge, right, near each other, right? So let me just draw that on the right. Okay. You have some positive charge, you have some negative charge, right? What is the electric potential energy between these two charges? Is it a positive or a negative energy if you put them next to each other? Can you guys remember how? I'm sorry?
Positive.
It's positive. Does it require, so so if I put two positive charge next to each other, right? It requires me to squeeze them into towards each other, right? That means I'm putting energy in the system. That means it's going to have positive potential energy, right? Just like if I have to walk up the stairs, right? I'm working against gravity to increase my energy, right? So if you have negative charge, do they tend do they tend to get pulled towards each other, or you have to be pulling away from each other?
They're both negative.
I'm sorry?
If they're both negative.
If one is positive, one is negative. Sorry, if they're opposite charge, right? So this will give you a positive potential energy, right? Basically, it'll, as as these two charges approach each other, the potential energy goes to infinity, right? Right. But if you have the negative situation, right, as the negative charge approaches the positive charge, it goes to negative infinity, right? In fact, you can just write this equation down, right? The electric potential energy between two charges is this electric constant Q1, Q2 divided by R, right? Divided by the distance between them. Okay. In fact, what in the atom, right? You can have you can have be on the left hand side, you can be on the right hand side. So typically, the way people draw these potential, right, as opposed to drawing it as R, they draw it as a function of X. So the electron is here, it'll have this amount of potential energy. The electron is here, it'll have similar. But then as it goes towards the center where the positive charge is located, right, it goes to negative infinity. Okay. Right? So you're basically digging yourself, as the electron get closer and closer and closer to the positive charge, you're digging yourself into a deeper and deeper well. Okay? And that's all you want to think about. You're deeper and deeper in the hole the closer you are to the electrons is deeper and deeper inside the well the closer it is to the nucleus. Okay? All right. So that's not, that's, stuff that we've probably seen in General Physics 1, right? But now if we have two atoms next to each other, what happens? Okay, I take one atom from up here, I take one atom from up here, put them next to each other. How does the potential energy of the electrons around them gets affected, right? So, right, you basically kind of stitch two of these wells together, right? And now the well looks like this. Hopefully it kind of makes intuitive sense. We're not deriving any of this stuff, okay? That's why we can go so fast, okay? Okay, you guys believe me? It'll look like that, right? So now, if you have an electron, right, it could be, at this energy, at this energy, at this energy, or down here somewhere, right? The interesting thing is that, well, let's just go with a simple model of like one proton, each of these atoms only have one electron. So now it's possible to have two electrons. Electron number one is maybe over here. Electron number two is maybe over here, right, at this energy. Right now you have two electrons, okay? And now the funny thing that, I'm not going to, I can't derive for you in one class. This is all of like, basically towards the end of modern physics, and I think even beginning of quantum mechanics, this is where it happens, where these two, um, these two electrons, they start off with with basically the same energy level, okay? But what happens is that if they are exactly the same energy level, they become this thing called a degenerate state, meaning they look the same from the outside, okay? And what happened is that these electrons will start to split in the energy to a different energy state, so to a different energy ground state, so that they are, each of the electrons actually have, there's actually a preferred lower energy state called EA, as opposed to this, whatever this was. Okay, and then there's a high energy electron. Okay, this is something I can't prove to you within just 2 minutes. Okay, but believe me, when the quantum mechanics happen, because the wave functions are overlapping each other, that happens. Okay, they become degenerate, but then the energy state gets split up. Okay, because of the electric field inside the atom. Okay, okay. So that's what happens when you have two atoms near each other, but in a piece of, let's say I take a little piece of silicon. This is not silicon, it's plastic, but I take a little piece of silicon, right? There are 10s to the 26 to the 27 number of silicon next to each other, right? So, let's say we do the 3, right? So if I draw the potential for 3 atoms, right? Let's do this even the same color coding, right? We got 1 potential well, 2 potential well, 3 potential well, okay? Actually, this kind of goes up further, right? So now we get 3 electrons, right? Initially, it had the same energy, E1, E2, E3. If they were, far away from each other, they have their own energy, right, that are the same. But what happened is that when they're next to each other, they get broken up into 3 different energy state, EA, EB, EC, right? Where this is the lowest energy state, lowest, okay, and this is the highest, and there'll be some middle one, okay? And for any system, okay, if you just leave it alone long enough, it'll tend towards the lowest energy state, okay? Right? It's just like me in my office. If you just leave me alone, I just take a nap, right? So I tend towards the lowest energy state also, okay? Same thing with electrons, right? Where, like, this is the most preferable state, right? The lowest energy, right? Most preferable, okay? Of course, when you have, a lot of energy together, right, you can start to see that, well, all these energy states kind of start to blend in together, right? It becomes this thing called a band, okay? Even though these are discrete, but then there's 10 to the 27 of them, right? So it just kind of looks really blurry, so it looks like a spectrum, okay? So when we have n atoms together, we get n number of degenerate states, and these are called energy bands, okay? Right, right. The other thing is that while each atom don't just have one energy state for its electron, right? It could have different energy states for its electrons in different orbits, okay? This is why the Bohr model is useful, where the higher and higher orbits, right? You're further and further away from the nucleus, and therefore you have a smaller magnitude in potential energy, right? Or a higher energy, right? Right? It's a smaller negative number. Instead of negative 13.7 eV, right? If you're at negative 1.02 eV, you're at a high energy level, right? Right. 0 is basically where you're taken off the atom and you're not even associated with the nucleus anymore. Okay. Right. So this degeneracy happens to the n equals to 1 state, n equals to 2, n goes 3, 4, 5. So there's multiple of these bands, right? Even just in a single atom, okay? Let's see, there's a picture of that, okay? Right, so this may be the n equals to 1, band gap, energy band. If you put 10,000, hydrogen atoms together, right? This will be the n equals to 2, this could be n equals to 3, right? Each of them have a different band, okay? One more vocabulary, right? The gap between the bands are called gaps, okay? Hopefully that's not too hard, okay? Right? Okay? All right. So, and the neat thing is that the more complex the electron structure is for your particular atom, right, the more bands you have, right? So for example, this guy, we're going to focus on this guy. This is a silicon atom. Okay. The way when you just take a bunch of silicon and just put them in a little petri dish, and then you just let it sit, they will form this kind of tetrahedron shape where you have four little balls on the side. I don't know if you can draw it here. You have the center one, and then you have four other ones around it, kind of like this. Hello. Four other ones around it. Okay. Right. So unfortunately, I don't have one of those fancy models, but one way you can think about this is that um, if I was the center silicon atom, right? This is one that I connect to another silicon atom this way. I connect to another silicon atom this way. I connect to another silicon atom this way, and connect to another one this way. Okay, it makes a tetrahedron. Okay, but the one of them is in the center. Okay, actually I should show you. I should just give you guys this link. You can. This is actually like a 3D model. You can rotate around. It's pretty cool. Okay, so the blue balls are what's called the primitive cell, and then it just kind of attaches more and more because the next actually I can demonstrate this, right? So if I connect to stick your right arm up, I connect to Matthew as my next silicon atoms, then Matthew can connect to Hasue and then Eddie and so on like that, right? Those are the other ones, right? Okay. All right. So the important thing is that, right, silicon has four bonding sites. Okay, four bonding sites. Okay, and the energy that the silicon can absorb is actually, instead of just discrete bands, it's basically a full spectrum. So this is the wavelength of light that silicon can actually absorb, right? So these are in weird units. Okay, so 1 micron is 1,000 nanometers. So like visible light is 700 nanometers down to 400. So visible light is around here. So silicon can absorb this type of light. Okay. All right. A little bit on the side on atoms. Okay. So now, right, let's think about conductor and semiconductor and what's the difference between the two. Okay. If we have a conductor, okay, what happened is that the outer shell, meaning one of my arms, right, has an empty spot for an electron to go to. Okay. For silicon, it actually doesn't. All four of my arms are full of electrons. Okay. Um, so what happened is that for a conductor, for copper, for example, a lot of our wires made of copper, there's actually like extra space, extra arms that has nothing in it, and then electrons just go there, and then that electron can get passed on to Matthew, Josue, and Eddie, and you can, if all of us have one arm left over, right, we can pass a ball around, right? That's what a conductor is. Okay, and there's this thing called a Fermi energy level, and I'm going to describe this in a little bit, but it's not very important right now for describing a conductor. But you can see the idea is that, oh, well, a conductor basically has empty holders that it can hold electrons. So if you have an electron here, right, it could pass it on to the next one, pass it on to the next person, next person, next person. By person, I mean the next nucleus, next nucleus, nucleus. Okay, okay. This is actually a time. It's trying to describe time for you, but I basically did it by just doing this. Okay. All right. There's another thing to think about. Okay. I'll ignore this side for now. Okay. You can also think about this in terms of what's known as holes. Okay. Meaning, if you have an empty slot here, right, you can think about it as, instead of thinking about it as a negative charge, you can think about it as a positive charge, right? That's actually moving backward up in the other direction. Okay. So negative charge moving forward is the same thing as positive charge going backward. And typically we actually think about it the other way, right? Negative charge going backward is the same thing as positive charge going forward. Okay? So conductors can do this, right? You can I have a free hand. I can pass my electron around from one person to the next. All of us has one free hand. Okay? Okay. A semiconductor like silicon, all my hands are stuck on other silicons, right? Right? There's no free hand, right? All four of my arms are stuck, arms and legs are stuck to other silicons. So they're not free to move electrons around anymore, okay? And that's why it is a semiconductor, okay, where the energy for electrons that are that are native to me. So silicon has 14 protons, so it should have 14 electrons, right? Silicon naturally will have 14 electrons, so it's always full of electrons already. You can't have, there isn't an extra, so my hands are closed, right? I'm holding 4 electrons on my arms and legs already. I can't hold another one, okay? So that's what this little band means. That means I have a full band, meaning all my arms are holding electrons. I can't go and grab another one, okay? In order for another electrons to join me, it has to jump into a higher energy level, okay? This is where the multiple energy level makes sense, okay? In order to get into another energy level, you have to jump up a gap, right? This gap that we just talked about, all right? And this gap, typically is empty, right? There's no electrons there, okay? But, right, and this is probably a good illustration of the different energy levels, okay? So let's say for silicon, there should be 14 little balls here, right? Because silicon is 14, yeah. So there's 2 electrons on n equals to 1, which is the lowest energy orbit. And then there's 8 on n equals to 2, which is the next energy orbit. And then there's 4 up on the spherical orbit, which is, so this silicon, with the green and the blue balls, right, they're all full, okay? For you to add another electrons to this, you have to jump into the n equals to 4. That's why it requires you to have more energy, okay? Right. So silicon is slightly conductive. This is why people talk about how silicon is sort of like, oh, it's a semiconductor defined as like, oh, it's a little bit conductive, but not very conductive, okay? The reason it's slightly conductive is because of this idea called Fermi energy, okay? So Fermi energy, so ignore these black dots up here, okay? Fermi energy means that, well, if I fill up n equals to 1, 2, and 3, right? Basically, that means, my silicon is full of electrons. It doesn't need any more, okay? But each of these electrons, right, has a little bit of wiggle in it, right? It's not at a zero, it's not fixed at a single point, right? It's still kind of buzzing around, right? And you can think about this as kind of like thermal excitation, where there's just some thermal energy just by being at a non-zero temperature. It's just wiggling up and down, up and down, up and down. And once in a while, it could jump up to n equals to 4, okay? And that's what this plot is trying to show you. And these plots are not really great because it's meant for like a year-long semiconductor class, okay? So this is the number distribution of electrons in a particular bulk solid, okay, where most of the electrons is in this blue part, right? Right? If you are at a 0 temperature, this will be the distribution of energy. So horizontal is energy, and then vertical is just number of electrons, right? You will get exactly this. But as you increase the temperature from absolute 0 to room temperature, for example, right, some of these electrons will start to bleed out, meaning their thermal excitation is allowing them to have a little bit more energy than they're supposed to, okay? And sometimes, right, when they get enough energy, they can hop to the next level, right? And there's a crazy calculation to calculate this probability, and this is something I actually give you a homework on, so just pay attention to this, okay? So just know what this equation means, okay? Right? So the probability, so P sub E means probability to be in the empty band divided by the probability to be in the full band, right? So it's this, what is the chance of an electron jumping into the next level? To calculate this, you take the exponential of negative, right, E plus E gap, okay, divided by KBT, and KBT, just take this number to be KBT, 1/40th electron volts, okay? Okay. So for example, if whatever is up here is 1/40th, is e to the negative 1. Okay? Okay? But for example, diamond, okay? Okay? And you can approximate this to be just basically e to the e gap, so you can ignore this this other part. Okay? Well, actually, it's not approximation; it's exact. Okay? Because these actually cancel out, right? Okay? So the band gap or the E gap for diamond, for example, is 5.5 electron volts. Not a lot of energy. Okay, very. It's basically 5 volts for an electron to cross a 5-volt potential. Okay, if you calculate this probability though, okay, you put 5.5 EV in here, right? That's where that goes. And then 1/40th, and then the denominator down here is e to the negative 220. Okay, that's actually, if you convert that to base 10, is 10 to the minus 96. Okay, so that's telling you is that the chance of a random electrons inside a diamond, carbon basically, a carbon crystal, right, to jump from its full band into the empty band, jumping the next energy level, right, is 1 in 10 to the 96. Okay, you're going to have a better time buying the lottery. Okay, for silicon, okay, you calculate the same thing. The energy gap for silicon is only 1.1. It doesn't seem like a big deal, right? Like, oh, it's like, 5 times less. But since this gets exponentiated, right, it makes a huge difference, okay? The chance for an electron to jump that gap is 10 to the minus 19. Still very small, right? But how many electrons is there for like, like a block of silicon? What will be approximately a number for that? 10 to what? What's a good number? 26, 27, yeah. Right? Because Avogadro's number, meaning 1 mole of silicon has 10 to the 26 atoms in it, and each silicon has 14 electrons around it. Usually it's actually the valence shell, meaning the outermost 4 that does this jump, because in order for this to jump, you have to jump 2 levels, right? So, right, usually this is probably multiplied by 4 or something like that, okay? Okay? So that's the number of electrons, and if 10 to the 26 electrons has, 10 to the minus 14 chance of jumping to the next level, some of them will make it up there, right? Okay? So that means, okay, the number of conductive electrons, and there's some factors that I'm not going to force you guys to calculate, is around 10 to the 9 electrons per cubic centimeter, okay? Okay? The thing to note is that this is for silicon, right? The number of conductive electrons in copper, for example, is 10 to the 23 electrons per cubic centimeter. Okay, huge difference between them. Okay, right? Copper very conductive, silicon not so conductive. That's why people define silicon as a semiconductor. Okay, right? So solids that are good semiconductors are boron, aluminum, silicon, phosphate, gallium, the stuff in this blue box here. Okay, tellurium, which is down here. Okay, it's all stuff on like on the right hand side of the periodic table. Okay, because the stuff on the left hand side, remember those are metal, right? The stuff on the right is the metalloids. That's what they're called. Okay. All right. I think I calculated these numbers for you guys already. Okay. So how? But this is not very useful, right? Having a bad conductor is not actually useful. You don't want to plug this in your phone, right? The reason you want to start with bad conductor is because you want to control its conductivity, okay? And this is where doping conductors is useful. And this is where this video explains things a lot better than I do. So I'll make sure the volume is high enough for you guys to hear it. Okay. So just in the picture of your head right now, right? Think about silicon, something in the center holding 4 electron balls, okay? And while connected to 4 other silicon by sharing electrons, okay? So I'm going to play this video, which is much better than what I would explain. Okay. This video is actually on transistor, and we're going to see the end of this next time when we talk about transistor.
The invention of transistors.
Okay. So hopefully it makes sense that what he described as the N-doped and the P-doped material, and be a little careful. When I first learned this, I thought P stands for positive, N stands for negative. It doesn't stand for that. It's very confusing. So the P-dope, right, it has an extra spot for electrons to get to, right? It has an empty hole, right? And when that hole is empty, the silicon is still, well, the silicon with the phosphorus, sorry, the silicon with the boron is still neutral, okay? It's not charged, okay? Neither of these stuff on the side are charged relative to, they're both neutral, okay? It's the fact that when you put them next to each other, right, the extra electrons that the phosphorus is holding, right? There's an extra electron with the fifth arm sticking out of their head, right? There's nowhere for it to go, but then by itself. But then the boron has a lack of electron in one of its arm, so therefore there's just a tendency for it to flow into that, okay? And when they're sandwiched next to each other, that's when they develop a charge that's negative on this side and positive on this side, okay? The p-dope and n-dope by themselves are not charged, okay? When you put them next to each other, that's when the charge develop, and it creates this depletion region between them, where it basically just have positive charge on this side and negative charge on this side, and it creates an electric field between them, okay? Hopefully that's clear, okay? That's one of the confusing point, okay, between them, okay? So as the video said, right, so p-type doping is done by adding boron. And why boron? Boron is here, silicon is here, okay? You guys remember why what sets the column on the periodic table? Right. So this has 14, right? So in this case, right, this has, remember the silicon has four valence electrons, okay? Okay, and boron actually has 3 valence electrons, and then phosphorus has 5 valence electrons, okay? And that's how they're ordered, right? Okay, so 3, 4, 5, and that's why if you go up one, you have an extra electron and you stick it in there, right? And then if you go down one, you have a lack of an electron, so it becomes essentially a positive charge there. So it becomes a hole that a negative charge can fill. I shouldn't say positive charge, okay? All right, so that's known as, so when you put boron, it becomes a p-type doping. And just to confuse it more, right, phosphorus, you would think that's associated with P, but it's not. It's associated with N-type doping, okay? All these stuff doesn't make any sense, okay? So don't try to associate them at all, okay? All right. So what the video just showed you, right, is that when you sandwich these two types of materials together, right, one of them has extra electrons that it wants to get rid of in a probabilistic sense. The other one has extra holes for these electrons to fill in, right? So what happened is that when you put them next to each other, right, some of the electrons from the N-type material will migrate over, just kind of in like a microsecond. So migrate is in pretty quick migration, because you're just traveling like like 2 nuclei over, right? So what happened is that in this case, right, now these electrons are over here, right? When you remove electrons from a material, it becomes positively charged, right? When you add electrons to a material, it becomes negatively charged. So this is even more confusing. When you put them next to each other, the N-type is positive, the P-type is negative. Okay? All right? So what happened is that then it develops an electric field. So this is a positive charge thing, so the electric field goes this way, right? Right? So therefore, you're going to have a high voltage point here and a low voltage point here, right? 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 So wherever there's positive charge, you have a higher electric potential, therefore higher voltage. Whenever you have a bunch of electrons, right, you have a lower voltage, right? Imagine just a capacitor plate, right? If you have positive here, right, then there's a potential between them, right? The voltage as a function of x, let's say, right? It's the same thing as a capacitor plate, okay? But these capacitor plates, you don't have to charge up, right? You just put them next to each other, and they naturally do this, right? Right. And this is what is known as a device called the diode, which is the first thing we're going to play with in lab 4. I don't think I need this H. So a diode looks like this. You can probably find some of those in your kit, right? It has a little orange color, has this little black band to it. The black band indicates the direction that the current is going to flow. Remember in the video, if you reverse bias a diode, no current flows, right? Only if you bias it in the correct direction, that allows you to flow, for the current to flow through, okay? Okay. In fact, there's a little graph. Oh, so here is the little diagram in a schematic, right? So it's just a triangle with a little blocker on it, okay? So current cannot flow this way, but it can only flow this way, okay? All right. Right. And typically, there's going to be a set voltage that a diode operates at, meaning you have to overcome a certain potential in order for the current to flow, right? And what happens is that when you make a diode, you can make it a 0.65 volt diode, 0.6, 0.3. You can make these numbers whatever you want. There's actually a light blue line here. It's kind of hard to see. Okay. The diodes we're using are these 0.65 types. Okay. So if you apply, right, 0 volts to it, what happens is that, well, no current will flow. So this is a current versus voltage graph, right? As you apply, close to 0.6 volts, right, let's say at 0.5, you start to see a little bit of tiny bit of current because you're decreasing that depletion zone between them. Okay, now like there's just some thermal fluctuation that allows you to the electrons to cross. But it turns on fully at 0.65 volts, right? This is what this blue line is, right? At 0.65 volts, basically the current will go to infinity, okay? And you don't want this, okay? Because when the current goes to infinity, basically you will pop you will blow the diode, okay? So whenever you're using a diode, okay, you're always going to have a resistor at the end of it or before it, and therefore it limits the amount of current that can flow through it, because otherwise it'll just pop the diode as soon as it goes over this threshold, okay? Basically because the current goes to infinity. Okay, let's not talk about the limitations. Well, just go quick, right? So even though it's supposed to stop all the voltage, if you reverse bias it, if you apply like 1,000 volts to it, it will allow current to flow. Okay, so don't do that. Okay. There's also these things called Zener diode. They're actually designed to break down at a certain voltage. So let's say this is positive 0.65 volts, right? Over here, it might be designed to be like negative 10 volts. So if the voltage go bigger than negative 10, then basically that Zener diode allows current to flow through. Okay. And when you make these Zener diode, it's a way to basically like stop those surge protector. They have Zener diodes in them too. So when the voltage goes too high, it actually allows the current to go to ground. Okay, and the symbol for Zener diode is very similar, but it was just, instead of the little bar, it's a little L shape there. Okay, and it'll take what voltage is supposed to break down at. Okay, so let me just show you guys a couple of I'm going to show you guys one simple diode circuit, because right, you're going to build this in the lab next week. Okay, this is what's known as a half wave rectifier, right? And the application for this is basically it's an AC to DC converter. Okay, so how does it do this? Okay, so let's say you have some AC source in here. You connect both of these, right? But you want the output to be DC. Basically, you want constant voltage as opposed to an oscillating voltage. Okay. Now we can make this is by just adding a little diode to your circuit. Okay. Right. So the way this works is that when let's just analyze this by looking at how this voltage is coming in. Okay. Right. When this voltage is high, let's say above 0.65 volts, right? The diode just kind of works as if like it's a short. Okay, it just allows current to pass through. Okay, so whatever voltage in here, the voltage output here, right, is going to be whatever the in minus this 0.65 volts, right? Okay, and this 0.65 volt is known as a diode drop. Okay, okay, but what happened is that, right, an AC doesn't just stay positive; it goes negative, right? So when it crosses 0.65 volts, right, it can no longer overcome that depletion region between the N and the P junction, right? So now this becomes a insulator. When it becomes an insulator, no current flows, so the voltage here becomes 0, right? So that's what happens here, okay, right? And then all of the negative side, right, all the negative side here, right, since it's reverse biasing the diode, right, no current flows, so all of this got chopped off, okay, okay, right. But once it comes back up above 0.65 volts again, now the current is allowed to flow, and that's what this blue part is showing you, okay, and it just repeats over and over and over again, and you're always going to get, you always have to pay this price of a diode drop, okay? That's why people design diodes that are even smaller than 0.65, but the ones we're using in the lab are 0.65, okay? It's not a very good constant voltage supply, right? As you can see on the graph here. It's still going up and down. We got rid of the negative stuff at least, right? At least it's not going negative, all right? So how can we improve this, okay? To improve this, okay, you can, I mean, just pretend this is an AC source, okay? You can add a capacitor, right, parallel to your resistor, okay? Why would a capacitor help? Okay, I'm going to go back up here. So if I add a capacitor to here, right, while the voltage is positive here, right, it's going to charge up this capacitor, right? It charges up this capacitor, right, and it holds that voltage for a longer period. In other words, I'm going to draw this. I'm going to try to draw this like this, okay? This is going to have a decay constant of 1 over RC. Remember that number? No, it's actually RC. Decay constant is RC, right? Right, that's tau, right? And then if you do the same thing on these, right, then the voltage becomes more constant, okay? It's still not that great, right? But if you add a big enough capacitor, I'm going to draw this. I'm going to draw the blue stuff again, right? Right. If you add a big enough capacitor, what will happen is that basically you kind of have this almost straight line, okay? Okay. The non-straightness of it, this is called a ripple or a droop. I think you're going to measure this in the lab, in lab 4, okay? Okay. So when you plug in your DC power supply from your laptop, for this little wire, for example, it's supposed to be 20 volts, but if you actually measure it on your scope, it'll kind of go like, you know, 21, 19, 21, 19, 21, 19, 21, 19. You can actually see this, okay? Okay? The bigger the capacitor is, right? Remember this RC, right? This R times C, right? If you have a bigger capacitor, the longer this decay constant, right? The straighter this line will be, okay? Right? But of course, the bigger the capacitor you got, the bigger power break you're going to have, right? Because the bigger the capacitor, the bulkier it will be, okay? So this is the circuit we're going to build in lab 4, and that's all we need to cover, okay? There are ways to improve on this. This is a better version of it. We're not gonna have force you guys make that because it's a more complicated circuit. But the idea is that instead of The one we just talked about is called a half wave rectifier. This is called a full wave rectifier. What it does, it also takes the negative voltage part and flips it upside down for you so you can get both. Okay, it's just a more efficient system, and that's probably what most people use anyway. Okay, all right. So that's all.